let's dive straight into this explainer of our source chapter, covering the fascinating evolution of how we store, manage, and protect data electronically. Today, we're unpacking the core concepts of database management, right from the fundamental texts on the subject. We live in a world completely overflowing with data, but as the source material explains, organizing it hasn't always been easy. We've got 5 main stops on our journey today: the limits of manual records, the flaws of early file systems, the introduction of the DBMS, database anatomy, and finally, the relational data model. Let's get to it. Section 1. Limits of manual records and the problem with pen and paper. To truly appreciate modern systems, you have to understand the sheer friction of where we started. Picture this. You're a teacher. You've got 50 students, and you have to mark attendance for 26 days. That means you are manually writing 1,300 distinct records every single month. Just marking P for present or A for absent becomes an absolute mountain of repetitive work. Those manual ledgers? An absolute nightmare. We're talking tedious entry, misspelling names, inevitable calculation errors. And think about this. What if you skip a record? Or worse, what if you spell coffee on the register? Poof! All that data is literally gone forever. There is zero backup. To find any historical information, you'd have to sift through a huge volume of physical, fragile papers. That brings us to Section 2, the file system flaws, or the flawed upgrade. So we tried to fix this manual mess by digitizing records into electronic file systems. We expected that just putting things on a computer would magically connect everything. But here's the reality. A student file and an attendance file were basically sitting on isolated islands. There was no automatic mapping between them. To make them talk to each other, a developer had to write totally custom application programs from scratch. It was incredibly inefficient. And what's really fascinating is how this flawed system actually bred a whole new set of headaches. Say you have 2 siblings attending the same school. In the old file system, their parents' name and address get typed out twice. That's data redundancy. If they move and you update one kid's file but forget the other, boom, you've got data inconsistency. Plus, try setting up security so parents can read attendance but not alter grades. Traditional file systems made that kind of access control incredibly difficult to pull off. Enter Section 3, Welcome to the DBMS, the ultimate problem solver. The hero finally arrives to save the day. A database management system, or DBMS, is a centralized system that logically relates our data. Think of it as a super smart translator. It provides an abstract view of the data, letting you interact with it simply while completely hiding the incredibly complex storage details happening on the physical hard drives. You don't need to know how it's stored. The DBMS handles all the heavy lifting, allowing multiple users to access a single centralized repository of data safely at the exact same time. And honestly, this technology is the invisible engine running our modern lives. Whether it's managing customer info and loan histories in banking, tracking land area for crop loans, handling warehouse inventory, or powering your online shopping cart, the DBMS is absolutely everywhere. It's the silent hero behind the scenes. Let's dig a little deeper with Section 4, Database Anatomy and Concepts. Time to define the jargon. First up, the database schema. This is basically the skeleton of the entire operation. It dictates exactly how the data is organized and related. It defines the table names, what type of data goes into each column, and all the strict rules. For example, a constraint in the schema might dictate that a mobile number column can only accept exactly 10 digits, no exceptions. Now, to keep track of all those rules and designs, the DBMS uses something called metadata. Simply put, it's data about data. Think of it like the index at the back of a textbook that helps the system know exactly where everything is located. It's the internal catalog the system uses to understand its own structure, ensuring that everything stays perfectly organized. And when you actually want to pull specific information out, you submit a query. A query is just a direct, precise request to the database engine. Instead of writing a massive custom application just to find out who was absent last Tuesday, you fire off a simple, quick query to the database and it retrieves exactly what you asked for. The relief this brought to developers was massive. Finally, Section 5, the relational data model, connecting the dots. Let's look at the most common framework. This is where it all comes together beautifully to eliminate redundancy. Instead of one giant, messy file, we split our data into specific tables. Take a student table, for example. It uses a unique Guardian ID, or GUID, to link out to other information. That little ID is the secret sauce. Before, you'd type a parent's address twice for siblings. Now, the student table just holds the student's personal info and that simple ID number pointing to the guardian.
Because of that ID, the guardian table only needs to list each parent exactly once. That ID mathematically links the parent right back to the student. In a relational database, each row is called a tuple, and each individual piece of data within that row is atomic, meaning it can't be meaningfully broken down any further. If a parent changes their phone number, you update it once in this table, and instantly the records for all their children are perfectly up to date. Goodbye inconsistency.
Now for a bit of quick terminology. In relational database terms, a guardian table with an ID, name, phone, and address has a degree of 4. Why? Because there are exactly 4 attributes or columns of information. The degree simply tells us how wide the table is. If we added a column for an email address, the degree would bump up to 5.
And let's say the system has 5 distinct records in it. We'd say it has a cardinality of 5. While degree is about the columns, cardinality is all about the rows. It's just a fancy way of asking how many distinct records are in the system right now. If a new guardian is added, the cardinality increases to 6. Simple as that.
Let's wrap up with this thought. As the source chapter wonderfully highlights, removing inconsistent data protects our memory, both in computers and in our minds. Moving from those painful manual ledgers to sleek relational models was a huge leap forward in protecting our most valuable information. So here's a question to leave you with. The next time you open your banking app or order a package online, how many unseen relational tables are seamlessly connecting in the background just to load your screen? Thanks for joining me on this explainer, and stay curious about the invisible structures powering our digital world.